Okay, thank you very much. So first, I would like to thank organizer and especially Dr. Sudhanshu for the invitation. So today I am going to talk on the heterogeneous catalyst. So we all know that we can employ thermal energy, solar energy, and the electrical energy, and then we use a solid substance or solid catalyst to convert them in useful chemical and fuels. So by employing these energies system, we can do this, but for their certain minimum requirement is also there. So in order to understand that, we need to understand the basic steps involved in the catalysis. So always we know that the basic step is the uh, diffusion of the reactant from the bulk to the active sites and the adsorption and then the desorption. In all these processes, what happened, the large surface area, porosity and active sites play a very, very important role. So when we are designing a catalyst, these are all things one has to keep in mind. But when we are thinking about the photocatalyst, then the substance should also have the light absorption capacity. Similarly, for electrocatalyst, the substance or catalyst should have the conductivity and the redox property to exhibit the Faradic efficiency. So that's what, so for example, in this, some of the representative figure, I just say that how the iron interplays the efficiency enhancement in terms of overall oxidation. Similarly, how the carbon dots influences uh, the reactions to catalyze even with LED light and so on. So when we are developing the industrial catalyst, the few things one has to keep in mind, that is the synthesis should be very simple, it should be scalable and reproducible, and we should always employ the economical catalyst precursors. A catalyst should exhibit the low deactivation phenomena. Most often it is better that if it doesn't deactivate at all, and it should be easily recoverable, recyclable, regenerable if it is required to regenerate. And when we are working with vapor phase reaction or certain thing where we have to change the catalyst in pellets and other form, then its porosity and reactivity should not change. So keeping that in mind, so how to implant the active site into the material? So one can implant the active site by following method. For example, one can incorporate metal oxide onto supported on different supports. One can introduce the active site by ion exchange if the material has the ion exchange capacity. One can employ the impregnation method, functionalization method, and in case of porous material, especially in zeolite, one can also employ the shipping bottle synthesis. So these are the various methods by which one can implant the active site into the materials. So now how the porosity plays an important role. As I mentioned that diffusion and the adsorption onto the active sites plays a very key role in heterogeneous catalysis. So porosity provide additional external surface area so that the active sites are more accessible, and it also help in the retardation in the deactivation phenomena. So today I am going to talk on 4 different kinds of porous material: metal oxide, Zeolite-MOF, and CCN4. So mostly I will deal how we can generate the porosity. So before generating this porosity, we need to understand how the materials are actually synthesized. So when we think about the metal oxide, we normally use the precipitation and co-precipitation method to prepare the metal oxide. Similarly, in case of silica, what we can use, that we can take some silica precursor, either we use the ethanol water mixture, we can employ the acidic medium or basic medium to get the silica nanoparticle. But these are the material are non-porous in nature. So how to impart porosity into the material? So always people need to think about the templates. So templates, mostly soft template or hard template. I will discuss a little bit about that hard template also. So soft template mostly are cationic in nature, anionic in nature, and non-ionic, or it can be neutral, mostly polymer based template. So they are generally employed to generate the porosity. Why it is employed? Because they have long chain, they also have the polar head group and non-polar group, so they can actually form the micelle in the aqueous medium and non-aqueous medium. So they can form micelle in the aqueous medium and non-aqueous medium, they can form the inverse micelles. So due to their different arrangement in the aqueous and non-aqueous medium, there are certain parameters which govern their crystallographic arrangement or their mesophase into the medium. So for example, critical micellar concentration and packing parameter. These are the two governing parameters which decide the which form of the phase will exist into the aqueous medium or their reaction medium. So the packing parameter decide it tells about the change occurrence of different phase, different mesophase, and it can change from one form to other phase as we have observed in certain case. So what happened using these using this cationic, anionic, and non-ionic surfactant, a large range of mesoporous silica materials have been developed during 1990 to 2000, and they employ all kind of ionic or non-ionic surfactant, and most of these things actually has the either electrostatic interaction or the hydrogen bonding. Through this hydrogen bonding, the surfactant are entrapped, and then after the calcination or by solvent treatment, after the synthesis, one can remove the surfactant and one can generate the porosity. So these are the way one can generate the porosity into the material, but these are all mesoporous silica. It doesn't have any active sites. So whenever we are thinking about the active sites, so always thinks that, okay, zeolites is a very well-known porous materials. So actually zeolite is very well-known porous material. It has been employed in almost all area of the life. So that, but mostly they are, everybody knows that zeolites are mostly used in petrochemical and fine chemical industry, and its application itself shows that how much zeolite framework is known, because there are more than 240 zeolite frameworks are known, and out of them 200 are lab synthesized and 40 are naturally occurring. So that itself demonstrates that how much successful story zeolite has. So today I am not going to talk more about it. I am mostly going to talk about ZSM-5, but beta is another interesting framework, because why these are important, because they are actually used in petrochemical and fine chemical industry widely. So I will just give you how the zeolites actually is synthesized. So how the zeolite is actually synthesized, you need to take the zeolite precursor, for example, silica and alumina precursor. Then you put into the synthesis composition of zeolite, where you have the basic medium. In presence of inorganic structure directing agent, it forms the secondary building unit, as is shown here, that these are the secondary building unit you can see here. And then after that, in presence of inorganic and organic structure directing agent, it forms the zeolite framework. And this zeolite framework is the seeds of the zeolites are formed, then crystal growth takes place to form the bulk form of the zeolite. So this is the steps in which you require both inorganic and organic template, but there are certain strategy or certain zeolites are known where you do not require the organic template. Inorganic template can provide this zeolites. So since there are several competing factors are there, so even till today, it is very difficult to say which template will give you which zeolite. So even till today, the complete mechanism of zeolites is not known. So if the zeolite is so important, that then it means our job will be very easy, but there are certain disadvantages. So what is the disadvantage of the zeolite is that either they have ultra micropore or they have medium and large pore. They are good for gas adsorption and the catalysis. But when we are dealing with the molecule which are little larger than the pore size, then the coke formation and zeolite deactivation takes place. So how to overcome this problem? To overcome this problem, we can insert the mesoporosity into the material. So how can we insert the mesoporosity? Either we should make an interconnected micropore mesopores, or one can reduce the size of the zeolite so that the pore length reduce and the deactivation phenomena reduce. In doing this process, what happens? We generate large number of surface selenol groups that will be also very good for the decoration of metal nanoparticle or metal oxide on the surface. So it means that can we use all those structure directing agents what we have discussed? No, it is difficult, because what it has been found that when the conventional structure directing agent which I have discussed are used in case of zeolite, it doesn't form. We got the separate phase of the zeolite. So what people tried, that it means that somehow these mesopore directors are not participating into the zeolite crystallization. So how do they will participate? So we need to force them to participate. So in order to do that, amphiphilic organosilane was designed, in which you can have the ammonium cation which direct the micropore, long chain which direct the mesopore, and this silane which bind with the silica and alumina precursor efficiently, and that's how they can participate in the zeolite crystallization. And we can see that you can finally tune its pore size, and the material can be synthesized in crystalline form. It also have the low angle XRD, so it is highly crystalline and highly ordered material. And you can see that especially for this cumene cracking and this isomerization reaction, it exhibit almost no deactivation case of cumene cracking, or in this case, the retardation in deactivation has been observed. Another strategy is that how can we reduce the size of the zeolite crystal, that is the mesoporous zeolite or nanocrystalline zeolite, in which we have intercrystalline pores. So how to do that? So if you see the silica structure, silica tetramethoxysilane or tetraethoxysilane, you have all the four sides for the growth. So if I cut one arm, then what will happen? The growth will be retarded. So commercially available N-alkyl triethoxysilane have been attempted to synthesize zeolites as an additive, and then what it has been found that it formed the mesoporous with very high surface area. If you can see that very high surface area and the mesopore volume is observed. And then if you see the catalytic activity difference, you can see that after incorporating the mesoporosity, the catalytic activity significantly improve, especially for the large molecular transformation. So then actually we have worked a lot on different kind of mesoporous zeolite and nanocrystalline zeolites, but I'm not presenting all those work. But the important thing is that while developing different kind of structure writing agent, what it comes out that most often whatever the structure writing agent it was developed, it is mostly produced the zeolite with disordered structure. Disordered means they will exhibit the wide angle XRD, but they won't exhibit the low angle XRD. So it is very important to have the material with having both the ordering. So we prepare a different multi-cationic structure writing agent based on the DAPCO. And when they have been introduced in the zeolite synthesis composition along with ethanol, then what it has been observed that the initial material had the hexagonal phase, and then it transformed from hexagonal phase to multilaminar phase, and then it formed the crystalline zeolites. So we have, you can see that you have the low angle ordering as well as the wide angle ordering. And one additional feature, you can see that you have the nanosheet morphology. This nanosheet is very important because it means that the zeolites thickness has been reduced in one direction. So I will give you another interesting work in which just now I said that for every kind of zeolite we need to have different kind of structure writing agent. It means that for every framework we need different structure writing agent. Then it is difficult because we are keep on developing different structure writing agent and we will getting one or other framework zeolite. So can we develop a strategy so that we can have zeolite synthesis by using the same structure writing agent, same mesopore director? So we employed the SDA1, which is commercially available, and then we employed the cooperatively self-assembly phenomena of two structure writing agent. What is microporous structure writing agent? One is mesopore directing. For example, when we added the equivalent amount of SDA1 and TPABR, we found very large surface area and external surface area and pore volume. And in this case also we observed the nanosheet-like morphology. Now I will explain why the nanosheet is observed. Actually, this is the framework structure of the ZSM-5. If you see that it has straight channel and a sinusoidal channel. So when you adding the SDA1 is preferred to locate into the straight channel, whereas the TPABR preferred to locate at the intersection. So what will happen? The growth along the B axis will not happen because of the hydrophobic interactions. It will only grow along the AC plane. That is why we are observing the nanosheet-like morphology in this case. And using this strategy, we could able to prepare ZSM-5, mordanite and sodalite. We have tried a lot to synthesize the mordanite, which is again very interesting zeolite, but we could not make any structure writing agent. We can give you the mordanite. Even people have not made any mordanite with this, any kind of structure writing agent for the mesoporous mordanite. So that's what, so it means that, so why we are developing zeolite? We are developing zeolite for the sustainable catalysis. So far, but the zeolite synthesis, especially the nanocrystalline and mesoporous zeolite synthesis, are not sustainable because we are using large number of structure writing agents. So can these structure writing agents will be replaced with the kind of a bio-based structure writing agent which are very sustainable? So we developed very recently a strategy in which what we have done, we have taken the silica and we have coated the starch on the silica. Okay, and then we employ this starch coated silica into the synthesis composition. What we observed that when we did not coated the starch, we required 21 days for synthesis. But when we added the starch over it, we only could able to do the synthesis in 6 days. Here, what we got the tri-level porosity. You can see here the mesopore pore size distribution. Inside here it shows the micropore, and this is shows the mesopore. You can see that it has the pore size distribution in the lower size as well as the larger size. Here we have the tri-level porosity where we have micropore, mesopore, and macropore. Again, the macropores are not micro in size. It is in the nanometer, specifically from 50 to 150 nanometer, which are very good for the catalysis. So you can improve the pore diffusion phenomena very well for the all kind of large molecule. And why this material could be able to synthesize in less time? This is reason that when we put in the synthesis composition, what happened? It formed the hydrogel, and your molecular precursor infiltrate into this molecule in this domain, and then the synthesis takes place here. So since there is no way this precursor can go out, so that's what their synthesis has taken place very fast in this domain because of the entropy factor, and that's what we could able to get the zeolite in very. And here we employed the micropore, that is TPABr. We employed TPOH, and we employed the propyl trithoxysilane as the mesopore director, and the starch here act as a macropore director. So here, using all these three combination, we could get this tri-level porous material, tri-level porous zeolite. And most importantly, this zeolite exhibited acidity very similar or better than the conventional bulk zeolite. Generally, when you prepare the hierarchical or mesoporous zeolite, their acidities are lower when compared because of the mesoporous in nature. But here we got the acidity somewhat similar or even better than the bulk zeolite. Now, so far I have discussed about how to introduce the porosity. Now I will discuss how you can tune the active site. So you know that zeolite can be synthesized mostly in aluminum form. Incorporating titanium and zirconium are little difficult because of the size mismatch and their hydrolysis rate of their precursor. But if you see that this aminolysis reaction means ring opening reaction, what happened? You can get selectively beta amino alcohol or alpha amino alcohol depending upon the amines and epoxides. So what happened? If you see that titanium silicate is having very low turnover frequency, but zirconium has very good turnover frequency. So it means that just by changing titanium to zirconium, why it is happening? Because zirconium has the very good interaction ability with the epoxide because of the its polarizing ability, because of the electronegativity difference between oxygen and zirconium. So it can open the epoxide ring, and then the amine which attack to the least hindered side of the carbocation and form the beta amino alcohol. But if your amine is more basic than the epoxide, then it will be attacking first to this zeolite, and then this nucleophile attached zeolite will attack to the least hindered side of the zeolite to get the alpha amino alcohol. So these are the two strategies when you can get the two different products selectively in this case. Another interesting example is that how to convert glucose to fructose. Generally, people employ the tin beta. Again, I will just tell you the synthesis of beta is somewhat difficult. And moreover, after the synthesis, you need to remove the aluminum from the framework, and then you have to incorporate the tin after the post synthesis. That is another challenge here. So that is what they are mostly employed for the glucose to fructose transformation. Another strategy is that you can also use base. Base also can convert glucose to fructose. If you can see here, the magnesium oxide can be able to convert glucose to fructose. But what we did, we prepared the magnesium silicate. What magnesium silicate impart? Magnesium silicate give the Lewis acidity. You can see that pyridine IR. It has Lewis acidity. It has very, very minimum Bronsted acidity. And because of this Lewis acidity and basicity, it exhibited very good selectivity for the fructose. Moreover, at high temperature, it can be converted directly from glucose to methyl lactate in very good selectivity. So same material, same catalyst can do this job because of the acidity nature. Since it material has both acidity and basicity, it can also be used for this condensation reaction. You can see that generally condensation reaction people employ two ketone or aldehyde ketone. What we have done, we have taken the furfural and we employed the isopropanol. So in presence of this acid base, it transfer hydrogenation takes place, give you hydrogen and this ketone, and this in situ generated ketone reacted with FAL to get selectively FAC. And if we take directly ketone, then what we'll get, we'll end up in getting F2AC. So that is what. So what we were interested in getting this FAC. That's why we adopted this protocol. So this is the how to introduce the different kind of acidity and basicity into a material, and then you can get selective catalysis. Similarly, Another interesting example that we just prepared zirconium phosphate. Zirconium phosphate, we prepared different kind of zirconium, titanium, and the tin phosphate, but zirconium phosphate was found to be very good, especially for the furfural conversion, furfural to furfural alcohol. Generally, this furfural to furfural alcohol, generally we employ the noble metal catalyst, but here we just did with the transfer hydrogenation employing the very economical catalyst. And again here what we observed that the adsorption of the furfural on the acid sites are very important. So if you see that here you have the Lewis acidity and also we have the Bronsted acidity. In case of titanium phosphate, we have somewhat stronger acid site. That's what it was not very good for this reaction. So here I have not shown, but titanium phosphates were not good for this reaction. Its activity almost 4 times lower than the zirconium phosphate. So what we observed that its adsorption was more in case of zirconium phosphate, and also it has the acidity which are very suitable acidity which are very good for this transformation. So moreover, since it has Lewis acidity and base acidity, so it can be also employed in canonical condensation reaction. Here again, if you see that the titanium phosphate was not good, but zirconium phosphate was good. Again, that what we observe here in this case that FAL can be converted very easy to FOL, means furfural alcohol. But if you employ if you use this benzaldehyde, the activity was not good. So this is actually because of the very good adsorption of the FAL over the zirconium phosphate. And in case of Bignelli product of this furfural, what we obtained that titanium phosphate is better than the zirconium oxide, because Bignelli reaction actually you required acidity, more acidity. So actually if you see that acidity difference, titanium phosphate was found to be little better than the zirconium phosphate. But at the end, if you prolong the reaction, both will exhibit the similar activity. But what I would mention through this, that in order to impart the desired activity, one should implant the active sites of the desired nature. So that's what is one of the example I have shown here. Now, mostly what people try that, okay, zeolites are generally known for the conventional catalysis, but we have employed this zeolite for the electrocatalysis. Zeolites are not very good electrocatalysts because they are not very good conducting, but they can have good conductivity because they have the ion exchange ability. Okay, so cerium oxide, actually, Dr. Deka has already discussed about cerium oxide. Cerium oxide has a very good property that it can store oxygen and release whenever it is required. Okay, and what is the problem with the methanol oxidation is that electrochemical methanol oxidation generally employed the platinum as a commercial catalyst. The problem with the platinum is that it gets poisoned because of the in situ or because of the intermediate product, that is carbon monoxide. But cerium oxide can convert this carbon monoxide to carbon dioxide efficiently. So what happened? We have the zeolite. Zeolite has the large surface area. It also has the surface enol group. It has the Bronsted acid site. So on this Bronsted acid site and large surface, we have coated the cerium oxide. Cerium oxide adsorb that zeolite adsorb the methanol because of the Bronsted acidity. Cerium oxide and also OH minus can be adsorbed on the zeolite, and that the cerium oxide convert to cerium hydroxide. And this dehydrogenation is actually facilitated by the cerium hydroxide. In a stepwise fashion, it gives you CO and then finally convert to CO to CO2. And if you see the catalyst deactivation phenomena, that if you see that in case of cerium oxide, this deactivation phenomena was low. We get the 96% retention in activity after 1000 cycle, where in case of platinum is deactivates very rapidly. Another work which we have done is that we know that the nickel cobaltite, nickel's NiCO2 is very good for the methanol oxidation, that we have already reported long back in 2013. But what we observed that nickel and copper both are good for the catalysis. So what we did, first we ion exchange the nickel and copper in suitable ratio so that it can be good for the methanol oxidation. So we did this also, and what we found that when we have 2 equivalent of nickel and 1 equivalent of copper, it will be very good for the methanol oxidation. But the problem with that the deactivation was observed. But when we implant Ni 0.5 Cu, 0.5 CO2, 30% onto this active support, then we obtained that after 1000 cycle, we got almost 99% retention in the activity, retention in their potential cycle stability. Whereas in case of platinum, it got reduced to 25% in 1000 cycles. So what you can observe here that in case of cerium, we got 96% retention activity, and here we got the 99% activity. So here what happened, the copper was important to lower down the overpotential. Nickel is very important to give you the NiOH species, which help in the methanol oxidation, and that's what we got more number of nickel into it, and that's what more oxidation ability and more current was observed. So now we have discussed that how to implant the active site into the zeolites and how they can be used for catalysis. Now for metal oxide, actually it is difficult to use the soft template based structure acting agent to synthesize the mesoporous metal oxide. So what people tried the hard template method. The hard template method is that you can take some template which are hard in nature, for example, Mesoporous, Silica or carbon, something like that you have to take, and then you have to infiltrate the metal precursor inside the pore of this hard template, and then finally you etch out this hard template. In case of silica, you can etch out with HF or with sodium hydroxide, you can get the metal oxide. So this is strategy actually people have adopted to synthesize the mesoporous metal oxide. But what we did, we dependent on the soft template strategy. What we have done is that we prepared the in situ resin, and this resin was prepared with fluoroglycerol and formaldehyde, and this interact well with F127, which is a block copolymer through hydrogen bonding, and then the metal oxide was there, metal precursors were there inside this cavity, and then after carbonizing and calcining, we get the mesoporous metal oxide. Please note that these mesoporous metal oxide are crystalline in nature, not the amorphous in nature, and their surface area and porosity was very good. So this is how one can generate the mesoporosity. Now I will, after this, I am going to discuss on the another interesting material, that is MOF. MOF is actually the material where you can use this material for the catalysis, but MOF actually people have tried that MOF is very good for the adsorption, especially for the gas adsorption. So with respect to zeolite, where you have only alumina and silica, they do not have any interaction ability with the metal precursor. So that is why they are not very good for the adsorption. But once you have that this MOF, so MOF will have the metal which can bind little bit more strongly to the reactive gases, so the adsorption capacity is good. But the little disadvantage is the MOF with the MOF is that they are generally unstable in the synthesis or when we are preparing the fine chemical. So, and another disadvantage or difficulty is that it is difficult to incorporate the mesopores into the MOF. So we attempted to synthesize mesopore MOF. So again, we use the same dicatonic structure acting agent, and we prepared the mesopore MOF. What you can see here, that the copper BTC MOF, mesopore MOF was prepared. This structure acting agent, dicatonic structure acting agent, formed the lamellar surfactant, and this copper BTC formed the coordination layer. And there, because of the weak electrostatic interaction, what I have shown here, it formed the mesophase, and that you can, since it is weak electrostatic, you can easily remove by solvent extraction, and you can see that this material has the mesopores. So we have the micropore and mesopore MOF, and it exhibited better CO2 adsorption and the catalytic activity for the bulk molecular oxidation, which has been shown here in this table. So as I mentioned that the MOF is very good. It's not that good for catalysis because it's generally unstable. So how can we make them stable? So we prepare the integrated Zeolite-MOF materials. So, and then we use them for catalysis. So what we did is that we took the beta. Beta is the material zeolite, where we functionalize the beta. You can see that beta is functionalized. COH group has been functionalized on the beta, and then we added the zeolite, this MOF precursor to grow the MOF onto it, or even with the NH2 MOF. I will tell you the difference between the UiO66 and UiO66 NH2. There is some difference in the stability. So we use this material. You can see that this is the TM image, beta zirconium BDC MOF, which is prepared with the functional beta. You can see that there's hardly you can distinguish the beta domain and the MOF domain. But in case of when it was not functionalized, you can easily distinguish these two domains. Okay, so now we employed these material for the selective catalysis. What we have seen that in gamma electron, which is again a very good solvent, which is for biomass. So you can take ethyl lemonate, which is produced from leonic acid, which can be produced from biomass. So this ethylene can be converted to gamma electron in presence of zirconium BDC-MOF. But if you take beta, you don't get this. You only get this trans-specified product. Please note that when you use the zirconium silicate, it didn't give any activity. It means that zirconium with the silica is not good. But zirconium with the BDC framework is important because ZR bond with oxygen that provide the suitable basicity, which is important for this cyclization. Okay, this cyclic, this intermediate and then cyclization. So if you see that when we added beta ZR BDC, we got the better activity and selectivity was improved. Please note that it is very difficult to incorporate more amount of beta. Only 6% beta was incorporated. If you take more beta, then the structure collapse. So that's why we were not able to incorporate more beta. 6 to 10% only we can incorporate. Another advantage I can show here in the biomass transformation, what we have tried, we tried to incorporate UiO66 into the MOF. And when we did this reaction with UiO66, what we obtained that the material was unstable into this DMSO medium, synthesis medium of this one-part transformation from glucose or sucrose directly to this compound. It was unstable, but UiO66 NH2 was not unstable, it was stable. So what we did initially, we took the glucose, it was transformed to HMF, then HMF converted to this. In one part transformation, it can be done through this because beta is very good for transformation from sucrose or glucose to HMF, which is not taking place in case of this UiO66.
Professor Rajendra, you have 5 minutes.
Okay, fine. So another important thing what we obtained is that, as I mentioned, that zeolite beta is very good for fine chemical industry, but the problem when you are using this zeolite, you need to remove the extra framework aluminum. Otherwise, your framework aluminums actually are enveloped with this extra framework. So you need to remove it, and so that, and that's then you can employ them in catalysis. So what we tried, rather than removing them, we use this extra framework aluminum to grow MOF onto the surface. So we added the MOF precursor, and then we grown the MOF onto the surface. You can see from the TM MOF has been grown, and then from the solid state NMR, what we have shown that the extra framework peak actually is got disappeared and is converted into the MOF peak. So that's the shift into the peak was observed. That was confirmed solid state NMR, TPD, and we have done some catalysis of this material. Now, MOF actually is not very good for catalysis, but it is very good to develop the different kind of catalytic material, which is not possible to get it directly. So for example, we prepare copper BTC and we convert it into the CuCO2. Actually, our group is mostly deals with the development of a catalyst which are economical. So we can replace this palladium-based catalysts which are used generally for the coupling reaction using this selective CuCO2 because you have copper 0 and copper 1, which are very good for this Sono-Gasera coupling reaction, and we can get very good CN coupling or CC coupling, and this CuO you can do for the oxidation reaction that we have shown. Another important example is that what now people are mostly working on single atom catalysis. Actually, single atom catalysis means you have to incorporate the nano cluster of the metal. So what we developed the silica we have taken as a template, hard template. We polymerize onto the support, and then we got that cobalt entrapped in this material in this framework, and then we did it for catalysis. That is again selective catalysis. How we have done selective catalysis? We have done the selective reduction and reductive end formulation. Actually, either you have to take hydrogen or you have to take hydrogen CO mixture. But what we have used the formic acid here. What formic acid has done? Formic acid can either dehydrogenation or dehydration can take place. So you can get in case of water, if you are using water, what you will get the H2 plus CO2, that will give you the selective reduction product. If you use the toluene, then you will get H2 plus H2O plus CO. So then you can do both. In this case, selectively, we got this one, reductive, only reduction in case of water, but in case of toluene, we got the selective reductive formulation. So this is how you can do the selective catalysis by employing very green formic acid as a reducing agent as well as the carbon releasing agent. Now, this is the last topic which I am just touching upon it is the graphitic carbon nitride, which is actually is a very important topic. And we just recently published one paper on the CO2 activation only with the graphitic carbon nitride. The beginners of this area can read this paper, especially the research student, they will find interesting. So actually I said that you can employ different kind of very economical reagent precursor to give you the this Ctn4, and Ctn4 you have different kind of site, and actually what happened, your different nitrogen changes how it's propagate in different directions. So the nitrogen type varies also. But this is non-porous. If you want to prepare porous, you again have to depend upon the this hard temperature strategy. So now generally Ctn4 is what? It's basic in nature. So what we tried, we wanted to incorporate both acidic and basic. What is our aim? Our aim was to do selective conversion of the epoxide to cyclic carbonate in absence of any co-catalyst or solvent. So we treated with H2SO4, exfoliation and re-precipitation has taken place, and we got the SO3H and NH2 group into the same material. And then since the CO2 was activated and SO3H and epoxide was activated simultaneously, so it given very good activity under very low pressure and solventless condition. Now, the main important for the Ctn4 is to use them in photocatalysis, because Ctn4 is very good for photocatalytic reaction. So what we did, we made the heterojunction of bismuth vanadate and Ctn4, and then what happened, you get the better photocurrent when you made the bismuth. But here the importance of this work is that we have shown through to the different control reaction, what we have proposed the mechanism, how actually it is happening. So it can happen either in OH cleavage pathway or CH cleavage pathway, or whatever the H2O2 is generating in situ, that can also give rise to OH dot radical. So that's how the mechanism has been proposed by studying the various photocurrent measurement, photoluminescence measurement, and other spectroscopic measurement. Similarly, what we tried, we know that very well that iron is very good for hydroxylation, and vanadium is also very good for the hydroxylation and oxidation reaction. So what we tried, we prepare iron vanadate and decorated over the Ctn4. Ctn4 is good for the light absorption. Iron vanadate is also very good for the light absorption, but also it exhibits the thermal catalysis. So here in this work, what we have demonstrated that thermal catalysis versus photocatalysis for a range of molecule from hydroxylation to for terminal oxidation. So what we shows that when we did the photochemical oxidation using the Ctn4 material, then we get the better H2O2 conversion. So actually this H2O2 is employed here as an oxidation agent. So you get better H2O2 conversion. H2O2 efficiency was better. Again, we did a lot of characterization, photoluminescence, EPR, and that terephthalic acid formation of OH dot radical and all. In situ UV visual we have correct. So we propose the mechanism through this one. And the final one is that very recently what we have done is that just yesterday, Professor Subramaniam also mentioned that one can dope the different material to tune the band gap. So we have done the photocatalytic CO2 reduction over Ctn4. Ctn4 has the ability, it has the band gap to reduce the CO2 to give you methanol. But what we have done, we have tuned the band gap by doping the carbon and oxygen through 2-methylamidazole. And we have proved that what kind of carbon species have been implanted, what kind of oxygen species have been implanted, and we have shown through how you can see that CO2 adsorption was better, CO2 binding energy was little reduced, and that's what we get the better CO2 conversion in this case. And actually the main reason is the band alignment when you have doped the CO. So it goes very close to the CO2 reduction band gap. That's what it's exhibit the better activity. So with this, I just want to conclude is that the templates are required to introduce the well-defined porosity. And if you want to do a particular reaction, you need to implant suitable type of active site. And if you want to do photocatalysis, you also have to introduce the material which should have the light absorption property, and then you can make heterojunction or you can make doping. And then large external surface area and surface functional groups were very important for the development of the electrocatalyst. And finally, in conclusion, that incorporation of the suitable active sites and optimum absorption of the reactant and product and optimum porosity all are very important to achieve the desired heterogeneous catalyst for a particular transformation. And this is my group. These are the students who have already graduated. These are the students who are working now. And I thank all the funding agency and the organizer for this talk. Thank you very much for your attention.